يعطيكم العافية. بنتابع حكينا عن الكوميونيكيشن الكترونكس. بنتابع بالintroduction. We will talk about the linear and some properties in communication system. طيب نيجي للlinear system و non-linear system. How we can distinguish between linear system and or non-linear system. Linear system is called linear if satisfied two properties, additively and homogeneity, or we call them together as a superposition. If an input x1 of t produces output y1 of t, and let x2 as an input produces output y2 of t, then when both inputs acting on the same simultaneously produces output like y1 plus y2. So we have it mathematically as shown in the slide. X1 give us y1 and x2 give us y2. So if we have an input like x1 plus x2, it should give us y1 plus y2. Then we will satisfy the property of homogeneity, which means that it is that if the input is scaled by any scalar like a or k, okay, then output also scaled by the same amount. So if we have x of t give us y of t, then k في x of t as k is a constant should give us k as a constant bel y of t. If these conditions does not satisfy, then the system is non-linear system. Now, let us study the effects of nonlinearity to understand it. Now, if we have a linear system like in the first figures and second one, if we insert one tone like cosine omega 1 of t to this amplifier, V output is equal gain مضروب في Vn. As you see, the output contains the same frequency component as input. They are just stronger because they amplify. Now, if we have two tones like A cosine W1 of t plus B cosine W2 of t as an input, V output will be the gain multiplied with the inputs. So we have both inputs are amplified by the same amount. So take the case when non-linearity applicable, like in the last figures, you have two cosine omega 1 of t plus b cosine omega 2 of t as an input. V output is going with the gain multiplied with V input, but the gain in linearity, it depends on the input. So we have different tones as an output are amplified differently also because the gain is depends or relies on V input, and new frequencies appear at the output, which we call them intermodulations, and we will study them later on. Now, time variance. A system is time invariant if a time shift in its input results in the same time shift in its output. Now, we can consider time variant system as a system whose output response depends on moment of observation or time of observation. In other words, a time delay or a time advance of inputs not only shifts the output signal in time, but also changes other parameters and the system behavior. Time variant system responds differently to the same input at different times. Now, if we talk about Laplace and Fourier transforms techniques, these techniques are not strictly valid for time varying system, but for linear time invariant systems, as we studied previously, we can apply them and they are valid for such a systems. Now, we can consider a system undergoing slow time variation in comparison to its time constants can usually be considered as a time invariant systems. So they are close to time invariant on a small scale as a bulk. Linear time variant systems are the ones whose parameters vary with time. Nonlinear for memoryless or static system. First, as you recall, a memoryless or static system does not need memory. It means it processes the input and output signals taking place at the same instant. So, the input-output characteristic of a memoryless nonlinear system can be approximated with a polynomial. So, we used to approximate it like in linear application, like y of t is equal alpha x of t, but using the Taylor series expansion, one can use it as model it as y of t is equal alpha naught plus alpha 1 x of t plus alpha 2 x square of t plus to a higher order and so on. Now, why we need a model, especially for nonlinear system? Models are representations that can help us in defining, analyzing, and communicating a set of concepts about the system. So, system models are specifically developed to support an analysis and specifications and design, then verification, and help us with verification and validation of a system, as well as to communicate certain information about the system. So in our case, we need nonlinearities often have physical origins, so we need to understand what's behind it as in physical origins. For analysis and computer simulation purposes, the physical phenomena should be described by a mathematical model. We choose to model the nonlinear system in our references or in this class by using a Taylor series model. As you see in the slides, Taylor series is very easy. V output is equal alpha 1 Vn plus alpha 2 Vn square plus alpha 3 Vn cubic and so on. Alpha 1 and alpha 2 and alpha 3, it is the first derivative of the V output over Vn at Vn equals 0. Alpha 2 is equal second derivative and the third derivative alpha 3 and so on. So the accuracy of this model is usually limited to the range of input level you insert. So typically we use to the third level in this class for handwritten, but when we using the computer simulations, we can go up with input level. Example about nonlinearity, RF amplifiers usually exhibit nonlinear behavior for large input signals, typically as shown below. So if you see in this slide, you can see we have an amplifier. We used to find the gain, it is minus GM fil R of D. Now, if you think about it, if you have the large scale V inputs, you're gonna go from linear region to what we call nonlinear region. So the gain will be changing or depending on the V inputs. So we will approximate this behavior with a Taylor series expansion as we see in the previous slide. Now, as we see in this slides, linear approximation, it is valid for limited input levels. So if we have our inputs in this region, the system will behave like a linear, and the gain will be just does not depend on V inputs, and it will be constant. But if we have the system increasing our large scale V inputs, we will have some trouble, so we will modeling it. Now in this slide, more terms should be added as we wish to extend the validity of the model, as you see in the figure. And here we added more terms to extend the validity of the model, as you see. So now the validity of the model is more acceptable than the first linear. Now, to study the effects of nonlinearity on the systems, let us consider the following system. As you see, x of t on amplifiers and y of t. Y of t is modeling by Taylor series, as you considered previously. Let us apply a single tune A cosine W of t to the input and calculate the output. When you calculate the output based on this model, you will get the following answers in the slides. You have the DC components, then you have the fundamental, and you have the second harmonics, then the third harmonics, as you see. And if you extend the level of the inputs, you will get more harmonics terms. Then from the following results, you can see that one can observe that even order harmonic results from alpha j with even j. It is the same for odd harmonics, and harmonic grows in proportional to a to power n, and amplitude of nth harmonic grows in proportional to a power to n. So the calculated, we defined the gain as the ratio of single levels at the same frequency. So we have the gain as V output at V inputs, but consider the V output, it is the amplitude at the same amount of frequency as the input. So it is considered alpha 1 plus 3 over 4 alpha 3 a square مضروب في a over a. It's give us as again alpha plus 3 over 4 a3 a square. From this gain, you can see that if we have alpha 3 as a 0 or does not count, we get back to this similar linear gain, which means that alpha 1. But in our case here, we consider it as a nonlinear system, and we have this gain. When we have a or the small input level is very small, the a square will be very small, multiplied with alpha 3 is very small, then we get it the linear behavior, which is the gain is a alpha 1. For larger input levels, depending on sign of alpha 1, alpha 3, gain may expand or compress. It depends on. If we have the sign of alpha 1, alpha 3 is positive, the gain may expand as you see in this slide. If we have the sign of alpha 1 multiplied with alpha 3 is negative, the gain will be compressed more and decaying to 0. 1 dB compression. Now, eventually, after a large enough input signal levels, the output power does not follow the input power, which means that we defined what we called 1 dB points. طبعا ال 1 dB points correlates well to loss of linear behavior, getting out of specification standards like EVM and ACPR, etc. So for linear applications, operations beyond this point is useless. Now, one can define from these figures, one can define a 1 dB compression points as the output power level at which the gain decreases 1 dB from its constant or ideal value. Once an amplifier reaches its power 1 dB point, it goes into compression and becomes a nonlinear device, producing distortion, harmonics, and intermodulation products. So amplifiers should always be operated below this point. Power 1 dB is one of the most important specifications for power amplifiers and amplifier in general, and it's up to this point that we consider an amplifier to operate linearly. Now, effective compression for FM الفيز modulation and frequency modulation and AM modulated signals. The FM and the phase modulation, they behave the same, and they vary the compression very well because they don't have any information carriers in the amplitude, so they tolerate compression. But AM contains information in its amplitude, hence distorted by compression. Why do we care about intermodulation? We have seen that communication systems often use available frequency band to transmit multiple channels for spectrum efficiency. Now, what happens to these signals when the transmitter exhibits nonlinear behavior? As we recall, nonlinear system or distortion results the systems to have intermodulation products, what we call it intermodulation products and harmonics. Now, to study the effects of intermodulations, let us consider the two-tone test or two-tone as an input for an amplifier and using the Taylor series models to model the nonlinearity of the device. Now, we have the two tones A1 cosine W1 of t plus A2 cosine W of t as an input for the amplifier. The output will be follow up with the Taylor series model as we spoke early. Now, as you see, we have a new harmonics and a new generated intermodulation models in the red in the slides. You can see them, they are very close to the fundamental frequency, and we have to have an ideal filters to split them. So, nonlinear distortion results from systems where the output signal is not exactly proportional to the input signal and harmonics or intermodulation products are generated. This impairment is introduced by the transceiver or the nonlinear behavior in the transceiver and needs to be considered. With nonlinear distortion, the application of a sinusoidal input, as we see in this example, results in a periodic output waveform that is not sinusoidal. Fourier series show that if you go with Fourier series to see the frequency components, the harmonics, superior harmonics are present. The result known being to be harmonic distortion or intermodulation distortion. Now, the fundamental components and the intermodulation products, I show them in the slides. As you see in spectrum, when you draw them in the spectrum, they are intermodulation, which means they are very close to the fundamental, and it is really hard to get rid of them. Now, intermodulation or IM3 products do not interfere with main tunes as you see in the previous slide. So why we should be worried with them? Now, we worried with them because we see multiple channels we send or we using multiple channels on a frequency band. So they will interfere with adjacent channels. Now, as you recall, intermodulation is a situation where it is a combination of undesired frequency components within an active system or from an external source. Combination of two or more signals will create another signal which may fail into another frequency band of the system and cause interference to this system. Now, intermodulation products are troublesome both in a transmitter and receiver. We can get rid of them if we strictly measuring the linearity and working just in linear region and avoiding the extensive use in diode and amplifier. Intermodulation characterizations. We generate, in previous slide, a test signal. For intermodulation characterization, we use two-tone test, as an inputs A1 cosine W1 of t plus A2 cosine W of t. Let us consider, without loss of generality, that A1 equal A2 equal A, and W or delta W is equal W2 minus W1. So if we rewrite the intermodulation components, we will get what we have in this slide. Our observations like frequency separation are the same, and before compression, main tunes grow with A, but intermodulation products grow with A power to 3. Now, intermodulation in general, as we speak before, occurs when two or more signals are used in a nonlinear system. So the spectrum at the output of a nonlinear device will not only consist of original signals, but remember, will also contain the sum and differences of input signals along with their harmonics. These new components will affect the adjacent channels. It might affect the adjacent channels, and it will be hard to get rid of it. Now, recall the B in B out plot, and let us draw the main tunes and the intermodulation third order products. Now, as you see in the figures, the first line 1 to 1, this line shows power of main tunes. The second line shows the power of IM3 products. Now, these lines indicates how much the IM3 products are lower than the main tunes in dBc. Now, dBc is the power ratio of a single to a carrier signal expressed in decibel. From the figure, if we measure relative IM3 to be minus 25 dBc at the output power of 20 dBm, what would it be at 22 dBm? The answer is obvious. It is just exchanges. So the answer will be minus 21 dBc. Now let us define a new terms, intercept point. Now the intercept point is obtained graphically by plotting the output power versus the input power both in logarithmic scales. Now the two curves as shown in the slide are drawn, one for the linear amplified, which is 1 to 1, and the second one is for nonlinear products, like the third one. If I ask you to find the intercept points of the third intercept points, you have to draw the one line for linear amplified signals at input tone frequency, and then another one for the third nonlinear product. If I ask you to find the second intercept points, you have to draw the line for linear amplified signal at the input tune signals with the second nonlinear product devices. So, how to indicate linearity of a system by just one number? If we wanted to indicate linearity or measure the linearity of the system by just one numbers, we have to find what we call third intercept points. The third intercept points, you can find it by extent and draw the projections of the cross point between the two lines you draw on the graph, as you see in the graphs on the slides. The third order intercept points means the signal most important specification of receiver's dynamic performance, because it predicts the performance as regards intermodulations, cross modulations, and block desensitization. So intercept points is very important in receiver. Now, third order modulation products are normally very weak and don't exceed the receiver noise floor when the receiver is operating in the linear region. But as input signal levels increases, forcing the front end of the receiver toward the saturation nonlinear region, the intercept points emerge from the noise, as you see, and begins to cause problems. When this happens, new signals appear on the band and self-generated interference begins to arise. So we need to warn the customer or to put specifications or boundary for input levels to not exceed this point. As you see in this slide, you can find the differences between, or measure the differences, almost the differences between a third intercept point input and the input 1 dB power. The difference between them at almost like 9.6 dB. And as you think, 1 dB, it is more harder to find than intercept points or input intercept points 3. Now, for a given input level, the IIB3 can be calculated by having the difference between the output fundamental and IM levels and adding the result to the input level, as you see in these figures. And please take big attention for this equations. Let us consider cascaded nonlinear stages. If we have two cascaded devices as shown in this slide, let's find the gain for this and the IIP3 total. By solving these equations like in this slide, you will come up, when you finish solving the two devices cascaded system, you will come up with this observation: the higher gain of the first stage, the more nonlinearity is contributed to the second stage. So the gain for the previous stage will affect the nonlinearity for the forward stage. To draw out the conclusion for cascaded devices, if each stage in a cascade has a gain greater than unity, the nonlinearity of the later stage becomes increasingly more critical or more important, because the IB3 of each stage is equivalently scaled down by the total gain preceding that stage. So in other words, we can say that in nonlinearity, the last stage will take the big attention for us to improve the nonlinearity, because the gain for the previous stage will affect this nonlinearity.